Good morning, everyone. So today we're going to talk about a topic that's going to be important to you for Project 2 Part B, which is heaps and priority queues and how they're related. There's going to be part of this lecture, Heapsort, that you're going to think is part of the project, but it's not, but it's very important. We've got a few notes up front here. First, about Project 2. Look at writing a small, simple program using standard priority queue to help you on Part A. Just put a simple, just a few values inside. Look at the test PQ.cpp that we gave you, and look at what it means when you put things, integers in and take them out. What order do you expect them to come out in? What does the default comparison mean for your priority queue order? Look at the papers on the priority queues, on the pairing heaps, and read the algorithm list card. When you work on, and I think this slide is a repeat, Professor Darden had this in the last deck also, don't leave pairing heap for the last minute, because it's difficult to do, it's all held together with pointers, and you're going to most likely have some seg faults, some memory leaks. Things are going to happen when you implement that are going to be less than perfect. But that's how we get better at using pointers. The meld function is used by basically all of the difficult functions. It's used by add node. Add node is used by push. And add node can be called completely independently of push. It's used by pop. It's used by update elt. It's used by update priorities. And your meld function, these are recommendations. It really, well, not all recommendations, it really does have to receive 2 node pointers. That's got to be done. And those 2 node pointers, in your mind, they should represent the root of a pairing heap, meaning those root nodes have no sibling, they have no parent or previous, whichever you decide to do. One of the things that says in the spec you have to do is decide whether you want to use a parent or a previous. Deciding on parent or previous doesn't affect you on whether or not you can pass the timing or memory. I have written 4 versions of pairing heap with different choices for, do I use a parent or previous? Did I use a 2-pass or a multi-pass pop? You'll know more about that when you read the paper. And the timings were not that different, but I chose the worst timing for the goal that you have to meet. It's just that once you make this choice, parent or previous, you must implement a few other functions. Really one really important function is going to be very different depending on whether you pick parent or previous, and you just have to make good choices in that function to make sure that you do it efficiently given your choice of what pointer you're going to use. Now, the return a node pointer, this is recommended. What most people want to do is they want to modify the root pointer of the entire tree. I recommend against that and just return node pointer. The reason is there's going to be functions like pop that are going to do lots of melds, but they only need to change the root pointer once. If you have meld always change the root pointer, it's going to be doing work that it doesn't need to do. Also, recommended. When you're done, you should have no test for null pointer inside of meld. Do it outside of meld. Not every function could give meld null pointers. There's basically 2 of them, add node and one other, which is update priorities. Those functions could give meld a null pointer. If they deal with it themselves and meld doesn't, then other things that use meld that can't have a null pointer can be more efficient. So if you have a null pointer check in meld to begin with to make sure that you don't have seg faults because of it, that's fine. Just when you're trying to get your timing down, you might have to remove those null pointer checks from inside of meld. There's one other thing. So after today's lecture, you're going to have almost everything you need for Project 2. There's one other function. I'll mention that at the end. Now we're going to do a little bit of review here from 280 on trees, and they're going to be important for today's lecture. And it'll also help you with a little bit of understanding of the parent heap also. So when you talk about a graph consists of nodes. They're connected by edges. If we want a tree is just a graph that is connected. It is less useful. It sometimes exists in the real world, but for most of our problems, it's going to be more useful if it's connected, if there aren't nodes that are not connected to anything. And it's also a tree is a graph that has no cycles. Now, alternately, definition 2 is an equivalent definition. We could say it's a graph where any two nodes are connected by a unique shortest path. There is a shortest path, there is no other path at all, and those two definitions are equivalent. Now, in a directed graph, we identify the parent-child relationships between nodes by these arrows, saying 6 is the child of 2. In a binary tree, if we restrict ourselves to binary trees, every node has at most 2 children. Now, when we create a tree, we have a node which we call the root. So here, 2 would be the root node. And when we start talking about creating this as an actual data structure, we would have something like a root pointer that points to the root node. Or we might implement this another way entirely. But regardless of how we implement it, we'll always have a node that's considered the root node. Now, the child of a node, we can see 6 is a child of 2. We have an arrow pointing to it. Whether the arrow points in both directions or not, we would still say that 2 is the parent of 6, whether or not we have a parent pointer or not. Now, if we look down the tree, if we look up the tree, any node that is a parent or a parent of a parent, etc., anything closer to the root along a path of edges is an ancestor. If we look down the tree, a child or a child of a child, etc., is a descendant node, as long as these two must follow a path of pointers. An internal node is a node that does have children. Leaf node is a node that does not have children. Now, one way we could implement this, if we were going to stick to binary trees, is we could make a struct. Now here I've shown it as a template so that we could have some generic item data type inside of it. We could make it more concrete. We can make it a template. The key is we're going to have that data inside, and we're going to have pointers to the children. Now, if this is a binary tree, we're going to have 2 children. If those node pointers are null pointers, then we might have no children. We would be a leaf if we have all of our children are null pointers. Aryan, would 4 be a descendant of 6? Yes. So in this example, 4 would be a descendant of 6, but 0 is not a descendant of 6 because there's no link of pointers to connect them directly. We have to go in one direction. So descendant is always looking downward, ancestor is always looking upward. So I know we're lagged by 30 seconds here. So I should have thought of this and done an example at the beginning. So yeah, so here, for example, so 4 would be a descendant of 6, 0 is not. 2 would be an ancestor of everybody. 6 would be an ancestor of 4. 0 is not an ancestor of 4. And we would also say, if I said, is 0 a descendant of 0, we would say no, because it's not a different node. So hopefully that cleared things up. I should have anticipated that and done it to begin with. Okay, so if we have our node structure here with our pointers pointing downwards, we've got a node, contains information, contains these pointers. We could, if we wanted to, also include a root pointer. That would take up a higher percentage of our memory for pointers, but we could do that. We could also have 3 children or 4 children, or a vector of child pointers if we wanted to have some sort of generic tree. Generally today we're going to stick to binary trees. When we come back to trees later on after the midterm, we're going to talk more about general trees. But today we want to stick to binary trees. When we have just the left and right pointers, if we don't have a parent pointer, we don't necessarily have an efficient way for moving up the tree. We definitely can move down efficiently, but it would be harder to move upward if we don't have parent pointers. Now that's not going to be an issue for us today. Now, also another concept is a subtree. Could we store the root separately? Well, we could have a root node without a root pointer, but then how would we represent an empty tree? So we tend to, when we're doing this with pointers, we tend to have a root pointer rather than a root, and then point to a root node so that we have an easy way to be empty. Now another idea here, which is going to be more important later on, but we're going to mention today, is a subtree. And this is really this is more important to you now because of pairing heap. So if I gave you, say, hey, I gave you a pointer P. P happens to point to 6. What's in the box here is the subtree starting at node P. So if I give you a pointer to a node, a subtree is that node and all of its descendants. So if I gave you, say, a pointer P2 that points to 3, then that would be the subtree rooted at P2. So we can think of this as a recursive data structure. Trees have subtrees, etc. I could say also, alternately, I could say that, say, if I gave you a pointer P3 that points to 0, well, this is the subtree rooted at P3. It's a tree containing one node. And if I gave you, say, 4 left, if I gave you a pointer P4 that points to the same place that 4 left does, that's a null pointer. It is an empty tree. Every tree has an empty tree that is a subtree of it. Now, we're going to have some properties here which are going to be important, and the definition here may seem a little bit counterintuitive at the start, but it's nice and consistent, and it's going to fit in well with something we're going to do later on in the semester. Now, if I ask you what is the size of a tree, well, it's by logic, it's all the nodes in the tree. So the size, if I gave you an empty tree, or equivalently, if I gave you a null pointer, you would say there's no nodes in that tree. Otherwise, the number of nodes in that tree is a recursive call to the size of the left pointer, plus a recursive call to the size of the right pointer, plus 1 for the node itself. So, for instance, if I gave you a pointer to F, so if I gave you a pointer to F, you would say, well, is that a null pointer? No, there's something there. So, recursive definition. Size of F's left subtree, which is 0. Size of F's right subtree, which is 0. We've got 0 plus 1 for F itself. we would say the size of the tree rooted at f is 1. Now, the height of a tree. Similar definition to before. If I give you an empty tree or I give you a null pointer, you would say the height of that tree is 0. Now, the height of a tree, what we're trying to get at really is how many, and if it's drawn nicely like this, how many levels are in the tree. But more than that, what is the height of any given node within that tree? Okay, so if I give you a null pointer, you'd say 0. If I don't give you a null pointer, it says take the maximum of the left and right, and that's I'm just going to emphasize our parentheses end there. So take the maximum of the height left and height right and add 1. Okay, so any null pointer would be 0 if I gave you a pointer to say g. Well, the height of the left subtree is 0, right subtree is 0, max of 0 and 0 is 0. We add 1, we'd say the height here is equal to 1. Similarly, any leaf node has a height of 1. They are subtrees which have a height of 1. Oh, wait, I forgot one. E. E has a height of 1 also. What about D? D has 2 subtrees. Both subtree is a height of 1. We already know that. So D has to be a height of 2. Same for C. C has 2 subtrees of height 1. Max of 1 and 1 is 1. Add 1 for C. C is at a height of 2. What about B? B starts to get more interesting. B has a left subtree of height 1, right subtree of height, left subtree of height 2, right subtree of height 1. Max of 2 and 1 is 2. Add 1 for B. B is at a height of 3. Now we can do A. Left subtree is height 3, right subtree height 2. Max of 3 and 2 is 3. Add 1 for A. A is at a height of 4. The height of the root is the height of the whole tree. So really the height tells us what is the maximum number of pointers you can follow before you end up at a null pointer. So think about this. If I started with the root pointer, I followed 1 link to get to A, not 1 link to get to A. I can follow up to 4 links from that root pointer. I follow a link to A, to B, to D, to H, and then I end up with null pointers. Now, what about depth? Depth is really trying to say, so if height is how far are you from the bottom, depth is how far are you from the top. So we say the depth of an empty tree or a null pointer would be 0. Otherwise, the depth of any node is the depth of its parent plus 1. Now let's ignore the fact that we drew this with arrows only going down. We can still have this logical idea of parent. So the depth of any node is the depth of its parent plus 1. So let's start at A. A has no parent. Because it has no parent, the depth of A's parent is 0, therefore the depth of A is 1. And I'm going to write this over to the right here for depth. I'm going to put it in purple here so we can keep them straight. So the depth of A is 1. The depth of B is the depth of its parent plus 1. Same for C, depth of its parent plus 1. So these are at a depth of 2. Everything here is at a depth of 3. Everything here is at a depth of 4, because it's always the depth of your parent plus 1. Now we're going to add a property here. We're going to add this property called complete, and this is going to be important later on today. So I've got a binary tree. Assuming I've got binary trees, we're going to do binary trees for the rest of today. Assuming I've got a binary tree, then a complete binary tree, every level except possibly the last is completely filled, and any level that's not completely filled, all the nodes must be as far left as possible. So we've got an example here of a complete tree that follows these rules. We've got two that we've labeled as being not complete. So if these are not complete, why are they not complete? Well, the middle one is lacking a node here. There's a hole. So this is, and when we said every level, we could have also said here every depth. So depth 1 is completely filled, depth 2 is completely filled, depth 3 has a gap in it, and there is a depth 4. So with depth 3 not completely filled, then we've got a problem because there is a depth 4. In William's question, is height and depth always the same? The maximum height and depth would always be the same. The maximum would always be the same. But for a given node, they might be different. So here, F has a height of 1, but a depth of 3. So for a given node, they might be different. But for the whole tree, the maximum depth and maximum height must be the same. Okay, so for this one, so that middle one's not complete because there's a gap in the next to the last level. In the rightmost one, this depth is full, that depth is full, that depth is full. In the last depth, I'm sorry I'm doing your job, EECS 281. I'm assuming that's Marcus, because I thought you had answered his too simply and you were done answering. Okay, so in this one, we've got every depth except the last is completely full. We haven't violated that rule, but there's a gap in the final level, and we're not allowed to have a gap in this level. If D was had a right child G, that would be fine, but having D have no right child makes it not complete anymore. So when we add nodes to a tree, if we always fill top to bottom, left to right, we'll have a complete binary tree. So we don't want to move on to a new level until this level's full, and when we fill a new level, we've got to fill it from left to right. Now the nice thing about a complete binary tree is that we can store it in an array without any wasted space. Now, for example here, we've got a complete binary tree on the left, and we showed the indices if it was one-based indexing. Why one-based indexing? We're trying to stay consistent with CLRS on this one because it is a good resource for this. It also makes our math work out a little bit better, and there's a couple ways to implement this. Remember, this is one of the data structures you have to implement for Project 2 Part B. The project spec has a set of suggestions on 3 ways to deal with the zero-based indexing versus one-based indexing. Now, it's going to make real easy examples also here when we figure out our formulas here. Now, one thing about the complete binary tree property is, like we said, it makes the array exactly the right size, the same as the number of nodes. Also, think of if we had gaps. If we had gaps, not only would we have wasted space, but we would also have to have a way to indicate, oh, well, there really is no node I in this tree. So we would have wasted space, and we would have to have memory spent on indicating which ones are there and which ones aren't there. Also, for the stuff we're doing today, it would make it more inefficient, much more inefficient when we get to what we're going to do with everything today with these complete binary trees and binary heaps. So, suppose I gave you this tree and I said, I'm thinking of a node I. So I'm giving you a node I, an index of a node I, and I want you to tell me what is the index of its parent. what is the index of its left child or right child? Does it? Maybe 4 would be a better question to do. 2 and 3 are a little easier though. 4 is really important though. I don't want to answer question 2 if this node is a leaf. It would be an invalid index. So what I want you to do is take a few minutes, think about this, type some ideas. What is the index of a parent node? What's the index of the left and right child node if they exist? And how would you determine if a node, if I give you an index I, how would you know if it's a leaf node or not? So work on those for a little bit and then we'll come back after I start seeing some answers. No, this one doesn't have anything to do with, well, it has a little bit to do with odd even, but it's not something we're going to worry about. We're just going to do the one-based indexing and we're going to keep the binary tree complete. Yes, there are some noticeable properties there, but we're not worried about them today. And I'm sorry if it sounds like there's a little bit of static over here. I've got lots of rain outside, so it might come over the microphone. Okay, well, we got one set of answers, so let's talk about these. So if I've got the index of a parent, well, if I say, let's look at some examples. I look at index 6, its parent is at 3. Index 7, its parent is at 3. So if we do integer I divided by 2, if we assume integer division, then that works fine. Okay, so the left child, so if we look at the left child, 2's left child is at 4, 4's left child is at 8, 3's left child is at 6. So 2 times I works for the left child, 2I plus 1 for the right child, if they exist though. So we want to know if we have any children at all. So really, we've got some right ideas there. We've got to check how I is related to the size. So it turns out for question 4, we have to not only give you I, we've got to give you the size also. So they're both important to figuring out number 4, which I should have written that to begin with. I wasn't trying to trick people on that one. Okay, so if we want to know if it's a leaf node, well, let's look at our indices here. So 4 has children, 5 does not, 6, 7, 8. So I've got 4 nodes that have children, 5 nodes that don't have children. So it looks like we're on the right track. It's got to be related to size times size divided by 2 here. So we want to be careful though, because integer division could give us a wrong answer depending on which way we go. So if I say here, if I is greater than size divided by 2, then that tells me, if that's true, that tells me I'm a leaf node. And this takes care of integer division. If we start doing 2 times I is greater than size, then or less than size, we might run into a little bit of edge case problems there. So I know this formula works that I wrote down. There's others, if we're really careful with our edge case of like even number of nodes, odd number of nodes, we could get other formulas that possibly work also. Now, here's one of the other nice things about putting a complete binary tree into an array. Not only do we have no wasted space, we don't need any space for pointers. We don't need the memory that those pointers would take up, and also we don't need a parent pointer in order to move up the tree. So if I give you an index 9, you can tell me where the parent is without a parent pointer. So not only do we not need the child pointers, we don't need parent pointers. Now, when we showed trees earlier on, let me go back one page first. Here in this tree, we've been putting things in here, and we've actually, some of these trees have been following a rule that we haven't shown you. Now, these are not binary search trees. Remember, in a binary search tree, we make a definition about nodes must be, like, if they're smaller, they must be left. If they're larger, they must be right. And we're not going to do that here. We're going to add a rule about where things are. And this rule is going to be called the heap order property. So what we're going to say is the priority at each node is no greater than the priority of the node's parent. So no node is allowed to have a priority higher than its parent. Alternately, no node is allowed to have a priority lower than its children. So you can't have a higher priority than your parent. You can't have a lower priority than your children. Now, if every node follows this heap ordering property, then we have a heap. And in both of these diagrams at the bottom of this page, we have a heap based on a different type of priority. So in the left tree, the priority is closer to the beginning of the alphabet is a higher priority. Alternately, we could say a lower ASCII value, because remember, A is defined as ASCII value 65 for capital A. So the root is still at the top, but we would call it the heap. So the top of the heap. So rather than the root of a heap, we call the top of the heap, which sounds good in English. So we have here A is at the top because it has the lowest ASCII value. And I defined the priority. I said high priority is small ASCII value. In the right-hand tree, which has integers, in the right-hand tree I said highest integer is highest priority. The highest priority is always at the top, but how we define highest priority can be different depending on what we want to do. So today we're going to make a heap. We're going to impose the completeness property because we really want to store it in an array. We can create a heap as long as we have the heap ordering property. We can create a heap, but we want to have an efficient representation. We want to be able to fit it into an array, or better yet, a vector, without any wasted space. So we need the completeness property to get it inside of the array without wasted space and without other inefficiencies. So given those two properties, we can make a heap, and we're also going to use a heap along with these properties to make an efficient priority queue. And we're also going to do an efficient way to sort, given all of these properties and our array-based implementation. So that's coming up. That's what we're trying to reach from all of this. So there's one other, the idea of a heap is, it's really, a heap is an abstract data type. It's something where you can get at the highest priority element quickly, but we're talking about a binary heap here. Now, rather than having to say, I have a heap where the highest priority is the highest value, or I have a heap where the lowest priority is the highest value, the shorthand way to refer to those is max heap and min heap. So when we say max heap, that's a shorthand way of saying the largest value is the highest priority. And when I say min heap, that means the smallest value is the highest priority. So that's a sort of a shorthand way of referring to them and quickly identifying what we have. So on the previous slide here, I'd say, two previous slides. So I would say the left-hand one, this is a min heap. And I'm getting sloppy on my writing there. That's supposed to be min, not mim. So that's a min heap, and this one over here would be a max heap. Okay, so we're going to use a binary tree as the underlying data structure. We're going to use a binary tree with this complete property and the heap property. We're going to use that to create both a priority queue and a heap sort. Okay, so before we get to the really cool stuff, we got to have some basic operations. So suppose that I gave you something and I told you this is already a heap, and we can verify that. So no node, every node has a lower, assuming this is a max heap. No node has a lower priority than its parent. We're not going to get to push yet. We've got to get basic stuff before we get to pushing. So if we assume this is a max heap, we can see it's a valid heap. What if I told you somebody changed a value in the middle? Somebody changed the value at index 8 from 2 to 35. So this 2 changed to a 35. Well, that's no longer a heap, but I want to fix it. I want to get it back to being a valid binary heap. So what we've got to do is we've got to check, have we changed it? Have we made it no longer a heap? So for example, let me just erase here for a second. If this 2 had become a 5, it would still be a valid heap. It went up in priority, but it didn't break the heap property. 5 is still a lower priority than its parent, and that's fine. But if I make it 35, now it is a higher priority than its parent, and that's broken the heap property. So how could we fix it? How could we get this back to being a heap again without changing any values, any more values? If we leave the values the way they are, but we want to get it back to being a heap, that 35 has to move up. So the 35, if we swap it with 9, so 35 moves up and 9 moves down, then we look again. Is 35 a higher priority than its parent? Yes, it is. That violates our heap property. So we would swap, move the 18 down, move the 35 up. Then we would check again. Is it a higher priority than its parent? No. So we don't have to move it up any further. It's very easy to do this in the tree representation, but really what's happening is behind the scenes, it's happening in the array. So that 2 became a 35. We compare it to its parent, which if this is index 8, the parent is at index 4. We swap them, so 35 moves here, 9 swaps down to there. Then index 4, we compare it to its parent at index 2. Oh wait, we swap those values, 35 and 18 swap. Index 2, we compare it to its parent at index 1. It is not a higher priority than its parent, so we have restored the heap property. And we can redraw it down here in the bottom right. So 81 is still there. 14, 1, and 5. That whole right subtree wasn't affected at all. We never even had to look at it. We've got a 35 here. We've got 18 there. 9 moved down to there, and the 4 and the 7 didn't move because they were in other parts of the subtree. They were not on a path of ancestors. we only have to look at a node and its parent, that node's parent, that node's parent. We only have to follow this path of ancestors going upward. So we've restored the heap property. Now, let's look at code to do that. Because really, remember, like I said, this is really happening in the array. So this is called fix up for two reasons. One is because a value increased in priority. Increasing in value isn't critical. If it was a min heap, we'd have a different situation. So increasing in value isn't what's important, it's that it increased in priority. Because it increased in priority, we had to look upward in the tree. So when something increases in priority, we look upward in the tree. Those are both related to the name fix up. We're fixing because a priority increased, and we have to look up in the tree to do it. So let's look at the code here. It says while k is greater than 1, wait, what does k greater than 1 mean? K is the index, so this is the index that changed. So someone said, hey, there's a heap here, and somebody at index k changed, and it not just changed, it went up in priority. So because it went up in priority, we're calling fix up. We'll do lower priority next. So because its priority increased, we called fix up, and we tell fix up, hey, here's the index of the one that changed. So if k is the index of the one that changed, and notice in line 4, we're going to change k. We're going to change our value. Remember, k was passed by value. So I'm not changing anybody's original anything. I'm just modifying k here. So k is the index of the one I'm looking at, and then it says I'm going to move up to my parent. So I'm going to move up to my parent as long as k is greater than 1, means as long as I'm not at the root. Because if k was equal to 1, I would be at the root, and node 1 doesn't have a parent. Remember, 1-based indexing. So because index 1 is the root, we want to keep going while we are not at the root. We might have to keep looking upward. So while we are not at the root, and heap sub k divided by 2 is less than heap sub k. So heap sub k divided by 2 is the parent. So we're saying while we're not at the root and the parent has a lower value than k. Now this code is specific. This code is specific to a max heap. Because here we compared values. Because we compared values, that comparison is based on a max heap. Really, we should be comparing priorities, and that's one of the jobs you'll have to do when you write this for Part B, Project 2 Part B. You're going to have to change this check to a priority check. And wait, I don't want to underline that because that looks like less than or equal to. Let's circle it. So the less than there is specific to a max heap. So we're saying while we aren't at the root and the parent has a lower priority than k, we've got things left to fix. We swap node k with its parent at k divided by 2, and then we move up. We say k divide equals 2. Remember, that's the same as saying k equals k divided by 2. We say move up to the parent index and check again, go back through the loop. While we're not at the root and you have a higher priority than your parent, you have to go upward. While you are not at the root and you have a lower priority than your child, while we're not at the root and the parent has a lower priority than the child, we have to keep swapping and moving up. If we reach the root, we stop. If we reach a point where we have fixed the heap, we stop. Notice in this example, we stopped when we got here because we weren't at the root. We're at index 2, we're not at the root, but when we compare is the parent, while the parent is less than node k, that part was false, so the while loop stopped, even though we weren't at the root yet. So the loop stops if we have reached the root, the loop stops if we've restored the heap property. So that's fix up. Now, what about if a value decreases? Wait a minute, before we do that, let's erase all our notes here. Let's talk about complexity. That's important. So, remember that we had to go upward here. We always go upward. We only deal with ancestors. We never look sideways. So we have to go upward, upward, upward. So the complexity of this while loop, at worst, this is O of the height of the tree. It could be less. We could get lucky. Like if we change that 2 to a 5, we'd look up one level, we'd say, oh, heap property is still good. We don't have to fix anymore. But at most, we would go from a leaf node all the way up to the root. Well, what is the height of a tree here? Couldn't the height of the tree be O of n? Couldn't the height of tree be n here? But wait a minute. We forced this tree to be complete. It means we don't have a stick. For it to be O of n height, we'd have to have a stick. We don't have a stick. We didn't allow that. So the height of the tree, exactly, Samaya. So the height of the tree is limited by the fact that every level is full. There's one node here, there's 2 there, there's 4 there. If the next level was full, there would be 8 and 16, etc. So the height of the tree is log n. So this thing is O of log n because that's the height of the tree. Now, it's on the order of log n. It could be something like ceiling of log n. We might have to, it might be log n plus 1 because remember we've got like the number of nodes and the height, etc. So we're not, this isn't an exact formula for the height, but it's definitely big O. It's in the ballpark of log n. So we might have to take a ceiling, we might have to take a floor, we might have to add one, but it's big O of log n is the height of the tree. And that's the complexity of this algorithm. We could get lucky and only have to check one level and see it's still a valid heap, or we might have to go all the way from a leaf to the root. Or another best case would have been we changed the root. The root changed from 81 to 91. We're already at the root. We don't have anything to fix. So it could be O of 1, but at worst it's O of log n. Okay, what if something goes down in priority? So we said here, what if heap at index 2, the value 18 changed to 3? So if this 18 changed to 3, and again, this is assuming a max heap. So with a max heap here, 18 changes to 3, it has decreased in priority. Well, now we've got to look downward. When we looked upward, we had a parent. We just had to look at the parent. Here, should I look left or should I look right? Who should I swap with here? Do I always want to do left because, hey, we want to make sure, we said nodes have to go left, correct? I could always go left, or should I always go right? Or maybe it's not based on position at all. Let's look at another example. Let's look at a counterexample before we finish this one. What if I changed this 14 to a 2? If I swap it with the left one, 2 goes here, 1 goes here, I still have an invalid heap. I've got a lower value 1 above a higher value 5. It's not a max heap anymore. So it can't be just the left, and it can't be just the right. I've got to swap with the highest priority child. So it's not left, it's not right. It's got to be the highest priority. So we're going to look at 3 and we're going to compare it to both children. We've got to look at the highest priority child. So we're going to swap it with 9 here. And then we do it again. Left, right doesn't matter here. We've got to go with the highest priority child. So 4 moves up, 3 moves down. Now we've reached the level of a leaf. We can't go any further down. We must have restored the heap property. Yep. Okay, so we did this on the array. In the array, 18 changed to 3. Then we compare 2 to its children. Its children are at index 4 and index 5. Biggest one swaps up, and this one swaps down into where that used to be. Then we do it again. Index 4. Oh wait, is index 4 a leaf or not? No, it's not. So it has children at 8 and 9. Biggest child is at index 9. The 4 swaps to here, and 3 swaps to index 9. When we're done, we can redraw it here. We've got 81, 9, 4, 3, and then the other nodes didn't get changed. So there's our tree when we're done and our array when we're done. So we need code for this. We had a value decrease in priority, and we had to look downward in the tree. So this is called fix down. So this is fix down because it lowered priority. We have to look down the tree. So in this one, remember to know if we're at a leaf or not, we need the heap size. So we've got k. K is still the index that changed. That really, I'll just draw it here, decreased in priority. So k is the index of the value that decreased in priority. We know the heap size and we know the container holding it. So now we've got a while loop. While 2 times k is less than or equal to the heap size. Okay, well, 2 times k is less than or equal to the heap size. What is that while loop saying? Remember our loop condition for fix up. When we did a fix up, we had to say while we're not at the root. Here we're saying while we're not at a leaf. So here we're saying 2 times k less than or equal to heap size. Remember I said earlier there might be other equations that would tell us if we're a leaf or not. So here we're saying while we are not a leaf. So while we are not a leaf, we figure out j, has some comments here for some of this, we figure out j is the index of the left child. We start there because if we aren't a leaf, we must have a left child because it's a complete binary tree. So we start at the left child, and then we've got an if statement, which I don't usually do ifs and what they do all on one line, but we had to fit this into one slide here, and we had a lot of notes at the bottom. So we say if j is less than heap size, and heap sub j is less than heap sub j plus 1. Aha! If j is the left child, j plus 1 must be the right child. So this if statement is basically saying if you have a right child and the right child is smaller than the right child is larger than the left child, then increment j should be the right child. So if you have no right child, this if does nothing, and j is the left child. If we have a right child and it's not bigger than the left child, we leave j alone, we're still at the left child. So if you have a right child and the right child is bigger than the left child, move j over to the right child. So after line 4 is done, we know j is the index of the larger child. In line 5, we check if heap sub k is greater than or equal to heap sub j. And the comment even says what we're doing. We're checking if we've restored the heap property, we can drop out of the loop, and really we could change that break to a return because we're done with the whole thing. We've restored the heap property. So if the node at index k is a higher priority, greater than or equal to the priority of its largest child, we can stop. If that's not the case, if we can't stop, we swap k and the larger child, and then we set k equal to j. We've got to move down the branch of the larger child. So we don't just move down, but we've got to move down into the correct branch. So if we look at our previous example, here we swapped 3 with 9, we moved down the left branch. Here when we swapped the 3 with the 4, we moved down the right branch and then discovered we were at a leaf node. So we've got to always move down the branch of the larger child, or alternately you could say we move down the branch that we swapped into or swapped with. So we've got to move down the branch that we swapped with, which is the branch with the larger child. So we keep doing this. If we ever reach a leaf node, we know we're done. If we ever reach a point where the heap property is restored, we know we're done. So this is fixed down. So what about the complexity of fixed down? At every node, we still have a constant amount of work. We've got to check if we do have a right child, we've got to check if the right child is bigger than the left child. We've got to check is the node bigger than its biggest child? If so, is the node smaller than its biggest child? If so, we've got to keep going. But we're going to go down, at most, we would go from the root all the way down to the lowest leaf node. We might get lucky and stop along the way because the heap's been restored. We might be lucky at the beginning because, if 81 had changed here, like if in the resulting tree, in this one, if 81 changes to 71, we look down one level and we're done. But we would never have to go more than the height of the tree. So this has got to be, I'll write it up at the top here, this has got to be O of log n also. Best case could be better, could be O of 1 in the best case, but in the worst case, it'll never be more than O of log n. So that's the upper limit, that's the upper limit on our complexity. It will never be worse than log n. So now we've got a way to increase a priority, we've got a way to decrease a priority. We now have the tools that we need to do everything else we want to do with a heap. So if we wanted to make this a priority queue, what we need to do is we need to be able to do push and pop and top. Top is going to be pretty easy here. The top priority is always in the root node, it's always at index 1. Top is pretty easy. So we need a way to push, we need a way to pop. And we want these to be efficient also, would be good. So we're going to need a priority queue for upcoming algorithms like shortest path, Dijkstra's algorithm, Prim's algorithm can use this also. It's also used for Heapsort, etc. So we want to look at how to do this efficiently. So if I did an insertion on this heap, remember, behind the scenes we've got an array, or really better yet, let's think of it as a vector, because a vector can always grow to make room for more stuff. Let's pretend that my vector has 9 things in it and a capacity of 11. How did it get to 11? That's what would fit on the slide, okay? We know that they grow by doubling. It really should be like 16, but I couldn't fit it in there. So let's just pretend that the size is 11. So in the underlying vector, remember, my underlying vector thinks it has a size equal to 9, and it has a capacity equal to 11. That's the underlying vector. So when someone tells me, hey, I want to push 100 into your binary heap priority queue, I've got to put that 100 in the vector. Where's the most convenient place to add something to a vector? At the end. So I do a data vector, my internal data vector, I push back the value 100. So it ends up there in the underlying vector. Where does that go in the tree, though? In the tree, it goes, I don't have quite enough room to do a straight line. We'll do straight squiggly arrow here. It needs to go to the left of 7, because remember, we fill top to bottom, left to right. This has got to be the left child of 7, has the value 100. Now, think of this as there was nothing there at index 10. There was no node there at all. It had infinitely low priority. Its priority then became something other than non-existence. It became priority 100. It has effectively increased in priority, which means we have to do a fix-up. So we look at, I'm going to change colors here, we have to look at 100 and its parent. If I had pushed the value like 3, we'd look at its parent and we'd say, oh, it's fine. It has a lower priority than its parent. It's still a max heap. So we look at its parent and we check, okay, is 100 greater than 7? So if it was 3, we'd say, oh, 3 is not greater than 7, we're fine. But 100 is greater than 7, so what do? We fix up, we swap. So 100 moves up and 7 moves down. Then we have to keep fixing up until we either restore the property or we get to the top. So we check 100 compared to 18. Higher priority than your parent, gotta swap. So 100 moves up, 18 moves down. Keep comparing to your parent. 100 compared to 81. Higher priority than your parent, we gotta keep swapping. So 81 moves down, 100 moves up. We've reached the root level. There's nowhere further to fix up, so we stop. Now, really this all happened in the underlying vector. So let's look at the underlying vector. So 100 was at index 10, its parent was at 5, so we swap 100 with 7. Then index 5, its parent is at index 2. Index 2's parent is at index 1. Okay, so that's what the vector looks like now. The tree, we can redraw the tree as long as we can put it in. We're going to have to insert a node at the bottom. I didn't quite leave room for it, but we'll get it. So we've got 100 there. We've got our 81 went there. We've got 18 moves over here. And now we need, again, a really sort of wiggly line there. Okay, so the left child of 18 is 7. And these other nodes, 9, 2, 4, 1, and 5, and 14, all stayed the same. Okay, so we've restored our heap property after an insertion. So after an insertion, we went from infinitely low priority to something that's not infinitely low. It had to fix up. So how do we implement that? Well, this would be a little bit different for an array as opposed to a vector. If this was a vector, I would just say, hey, let's do a data vector, or let's call it, and this is more consistent with Project 2 Part B, I'd say like data vector, push back this new item. If this was a vector, I wouldn't even have heap size. Do not create, when you do Project 2 Part B, binary heap, don't add a variable for the size of the heap. The vector knows its size. And then we call fix up. We know the cost of step 2 is amortized O of 1. So we've got an amortized O of 1 for the vector push back. followed by the fix up, which we know is log n. So we've got line 2 is amortized O of 1 plus O of log n for the fix up. So this thing is O of log n. It might have to go all the way to the root of the tree, or it might stop after 1 or 2 or 3 fixes. But it will never go longer than the height of the tree. So this is our complexity of priority queue push is log n. Now, what about popping? So someone asks me, who's at the top? I say, ooh, well, index 1 is a value of 81. Top is easy to answer. Pop, though, we have to get rid of 81. But the beginning of a vector is not a good place to erase from. In fact, vectors don't even have a pop front. They have a way to erase a particular iterator, but it's inefficient because everybody would have to move over if we got rid of 81. And it might not be a heap anymore. If I swap the 18 and 14, it's still a heap before 81 is deleted, but if I delete 81, then 14 would become the root, and it's not the root. So we can't do that. We can't just get rid of 81. Where's the most efficient place to get rid of something in a vector? Most efficient place is the back of the vector, because really right now I've got a size equal to 9. I've got a capacity equal to 11. If I tell a vector to pop back, all it really does is change the size. But that would get rid of 4. I don't want to get rid of 4. I got to keep 4. So let's replace, not swap. Swap would be a waste here. I'm going to replace that 81 with 4, and then I'm going to pop back in the vector. The vector now says my size is 8. You're not allowed to look at this anymore because square brackets won't let you. It's not valid. So we're going to replace the 81 with 4. Could I have swapped them? Sure. Does it matter? No. What does it take to swap? To swap, I've got to say temp equals A equals B equals temp. That's 3 assignments. If I just say replace the front of the vector with what's at the back of the vector, that's 1 assignment. That's O of 1. So I'd rather do 1 assignment than 3 assignments. They're both O of 1, but it's a better O of 1. It's a lower constant. So I replace the 81 with the 4. I pop back on the vector. Well, the problem is now this node doesn't exist, and this node has a 4 in it. I've done part of the pop. I've gotten rid of 81, but I've violated the heap property. 4 is a lower priority than its children, and that's not valid. So we have to fix, and we have to fix down, because effectively 81 changed its value to 4, and a node disappeared. So because 81 lowered its priority, we must fix down. So we start comparing. 4 compared to which one? Oh yeah, the largest child. So the largest child moves up and 4 moves down. Then we compare 4 to its children, 9 and 7. The larger child, 9, moves up and 4 moves down. So now we compare the value 4 to the largest child. Well, there's only 1 child. We still check though. Wait, 4 is now it's not a lower priority than its child, so it has restored the heap property. In terms of the array, so 4 swaps with 18, then 4 swaps with its child at index 4 or 5. Largest one is at index 4, so 4 goes here, 9 goes there. We check index 4 versus its only child at index 8. No swap is needed, and we've restored the heap property. We can redraw it. 18, 9, 4, 2, that node is deleted, and the 7, 1, 5, 14, that section of the tree was never involved. All right, so we've done a deletion. So what we're going to do a deletion is we're going to replace a value with another value. We reduce what we think of as the current size of the heap, and we call fix down. We've got an O of 1 operation followed by an O of log n operation. So this whole thing is O of log n. It could be better. We could have had a tree full of 5s. It's 5s everywhere. I replace a 5 with a 5. I notice that there's nothing to fix, so I don't have to go down any levels to fix it. Or maybe that value was a leaf, but it was the biggest leaf there was, and so I wouldn't have to reach the level of the leaves to fix everything. So deletion is log n. So we're deleting from our priority queue. We have to delete from our underlying binary heap, and we have to restore the property. Now you can make sense of a whole new XKCD that never made any sense before. Okay, so we'll move on from that. You can laugh at that one later. All right, so now we've got a new task. Suppose I gave you a collection of stuff, and I said, turn this into a heap. Well, we could say, well, hey, let's just start with an empty vector and let's just do push one at a time. If I do n pushes, none of those pushes is worse than log n. That's n log n time. And that's decent, but we could do better. So suppose that you've got like an array, or you've got a vector, and it's filled with values, and I want to turn that into a binary heap. I could do it in n log n time, but it would also take me an extra vector because I've got to take the ones out of yours and push them into my empty one at a time. What I could do also is I could say, hey, let's sort this in reverse order. If I sort it in reverse order with the highest priority value at the beginning, that is a heap. It's a very specific version of the heap, but it is also a heap. That's n log n also, if we use like STL sort. Now, we could also use what we've got. We've got tools. Our tools are fix up and fix down. I could treat your existing array or vector as if it was a heap that just needs some fixing and do some fix ups and fix downs on it. Now, I could proceed from bottom to top or top to bottom. Now, when I say bottom to top or top to bottom, what I really mean is highest index to lowest index. Oops. Highest index to lowest index would be what I mean for bottom to top. Highest index would be the bottom, the top would be at the lowest index. So I could go from highest index to lowest to smallest index, or I could go from smallest index to largest. And that's what I mean by top to bottom, would be from the smallest index would be the top, the root, to the largest index. Now, so I've got two directions I can go. I can go bottom to top or top to bottom, and along the way I could apply either fix up or fix down. So that gives me 4 possibilities. I could do bottom to top fix up, bottom to top fix down, top to bottom fix up, top to bottom fix down. So that gives me 4 possibilities. Of those 4 possibilities, 2 of them don't always work, and of the 2 that do always work, they have different efficiencies. So we've got these on If we were in person, I'd have you look at this and think about it a little bit more. But we don't have a good way to do feedback here. Generally, when I do this in lecture, we're getting near the end of time here. So what I'm going to do is I'm going to show you our hidden slides. So what we can do is we can take the one you've got and we could do bottom to top doing fix down, and it says it's O of n and it works. This is what STL, standard make heap, does. If you give it like 2 iterators, it's going to be doing this. It's going to go from bottom to top and it's going to do fix downs. Now, if you do bottom to top doing fix up, it doesn't always produce a valid heap. Sometimes it does, sometimes it doesn't. Here's an example of if that was your starting array and you did this, it would end up in an invalid heap state. I could go top to bottom doing fix down. It doesn't always produce a valid one. Here's a counterexample. I could also do top to bottom doing fix up. It works. It's a valid heap all the time, but it's O of n log n. So these two work, and this one's got the better complexity. Now, the proof is a little bit ugly. What I'm going to do is I'm going to give you a hand-wavy proof for this. So if we do bottom to top fix down, so what I'm going to do is I'm going to make a table here. I'm going to make a table to prove this to you. So what I'm going to do is I'm going to have, we're going to have the number of nodes at a given level of the tree. So how I'm going to have number of nodes, and I'm going to have the number of levels to fix down. And the last column is going to be the product of those two values, because that would be the total amount of work in that level, or we could say in that depth. Okay, so because we remember this is bottom up, starting at the bottom of the tree, calling fix down. So we've got nodes that are leaves. About how many nodes in our tree are leaves? Remember, we had an example that had 9 nodes. It had 4 internal and 5 leaves. If we had a bigger tree, we would see that about half of the nodes, approximately half of the nodes, are leaves. Now, when I say bottom up, remember we meant bottom to top. When I say bottom, I don't even have to call fix down on the leaves, because I know fix down on the leaves will immediately finish. So I'm going to choose my starting index. Remember when I said bottom up, I said highest index to lowest index. Well, really, we're going to go from the highest index with children. Highest index with children, I'm going to skip these entirely. I'm going to start at the highest index that actually has children. So no work gets done there. How many nodes are above the leaf nodes? Well, think about it as a binary tree. Think of it if it was complete. If I had a level that was completely full and had like 8 nodes, if everybody had 2 children, there would be 16 nodes below it. So if there's 16 leaves, there were 8 parents, there are n over 4, and n is the total number of nodes in the tree. So of the number of nodes in the tree, half of them are leaves. A quarter of those nodes are just above the leaves. How many levels do we have to fix down? 1 level before I reach a leaf node, and leaf nodes don't need fixing. So I only have to fix down 1 level. That's n over 4 work. Above those, there are n over 2 nodes. They have to be fixed 2 levels. The product of those is 2 times, n over, I can't even think straight here. I'm trying to work ahead and think ahead and do the problem here. N over 8, sorry. If there's n over 4, there's n over 8 above those. If I fix 2 levels, the product of that is 2 times n over 8, which is n over 4 also. Below those nodes, there's above those nodes, there's n over 16, which involves fixing 3 levels, which is 3n over 16. There's n over 32 below those that have to be fixed 4 levels. That's n over 8. We're getting diminishing values here. Then I'd have n over 64. There'd be 5 levels to fix. That's 5n over 64. That's basically 1/16. Eventually, I'm going to get to one node. That's the root. How many levels needs to fix? Log n. Now, what's the sum of all of this? This is where the hand-wavy part comes in. Well, I've got n over 4 plus n over 4. That's n over 2. I take n over 2 and add a quarter to it. I then take and add an eighth. I add a 16th. That's n. Plus log n. So the sum of that thing is equal to n. So if I sum all that up, I've got n. So my total work is n for everything but the root. The root takes log n. N plus log n is O of n, is how long this takes. So that's our hand-wavy proof why the bottom-up fix down is O of n. You can use this same sort of hand-wavy proof for this method, top to bottom, doing fix up. What you'll find is you have the root node. There's only one node that gets fixed 1 level. There's 2 nodes that get fixed 2 levels. There's 4 nodes that get fixed 3 levels, etc. And the products get bigger and bigger instead of smaller and smaller. So you'll get an n log n out of that. Okay, let's try this together. So what we're going to do is we're going to draw this and we're going to treat it as if it's just a heap that needs a bit of fixing. So let's draw it. We've got 4 is effectively the root. We say let's assume it's a heap and do some fixes. So 4 has children 2 and 5. So I'm going to draw some lines here to get my levels 1, 2, 3, 4. Okay, so the level before that is 1, 7, 9, 14. And then the level below that is 18 and 81 are the children of 1. Okay, so we got to do a bottom-up fix down. So we start at the highest index that has children. Now remember, our indices are 1, 2, 3, 4. Index 4 is the highest index that has children. So we do a fix down on 1, or really on index 4. Okay, so largest child, 81, moves up. So 81 moves up and 1 moves down. And that's it. We've finished that fix down. Now we've got to do a fix down on index 3. Largest child, 14, swaps with the parent. I've reached a leaf level. Fix down is done. Now I do a fix down on, I'm going to change colors here. I do a fix down on index 2, which happens to be the value 2. So 2, 81, and 7, I fix down. I choose the largest child to move up. So 81 moves up and 2 moves down. I'm in the middle of a fix down though. I got to keep going until I reach a leaf level or restore the heap. 2 children are 81 and 1, or sorry, 18 and 1. 18 and 1, 18 moves up, 2 moves down, and I've completed my fix down there. Now I'm going to have to redraw this. So I've got a 4. 4 has children 81 and 14. 14 has children 9 and 5. 81 has children 18 and 7. And 18 has children 2 and 1. All right, so now we need to change colors again. We need to do a fix down on index 1. So we do a fix down in index 1. Okay, we pick the highest priority child is 81. 81 moves up, and 4 moves down. We're in the middle of a fix down though, got to keep going. Highest priority child is 18. 18 moves up, and 4 moves down. Highest priority child is 2. We've restored the heap property, so we're done fixing down, and here's our final tree. 81, 18, 14, 9, and 5, and then we've got 18's children are 4 and 7, and 4's children are 2 and 1. So that's the completely fixed binary heap, and although we had to redraw it twice, it really only took O of n time. So there's our final tree. Now, the last thing we're going to do today is heap sort. Now, this is not in Project 2 Part B, but it's important to understand because it's a very important sorting algorithm. So what we're going to do to sort with a heap is, we're going to say, hey, I've got a heap. If I've got a valid heap, I know the highest priority element is 81, but normally when I sort, I would like the biggest element to be at the back. I normally want ascending order. So you'd say, well, wait a minute, this is almost sorted in reverse. Well, almost sorted isn't sorted. So what I do know is, though, this is the biggest element. What I'm going to do is I'm going to swap it with the back, and then I'm going to draw a line there. I'm going to say you are no longer part of the heap. You are part of the sorted region. Now I must fix down on everything but the last element. So let's draw it in the tree, is a little bit easier to see. So I swap, I just swap. I don't look at values. I just do a swap, 81. But now this 81 is sorted. It's not allowed to be fixed down. So let's change colors and do a fix down. So 81 has changed priority. It's become 1. It lowered its priority. I must fix down. So I find the largest child, 18, and swap with it. Okay, I'm still in the middle of a fix down. I find the highest priority child and swap with that. I'm at a leaf node. I'm done fixing down. So now let's redraw our vector. I've got 18. I'm just going to rewrite all the values here. So I've got 18, 7. I'm just going to put commas here so we can definitely see where they end and begin. 14. 4 didn't change. I've got a 1 there. 9 and 5 and 2 didn't change. And there's an 81 that is set aside. It is not part of the heap anymore. It's part of the sorted region. Now, we change colors. We repeat that process. So we swap 18, the root of the heap, with the last thing that is part of the heap. So we swap the 2 and the 18, and then we move our line. We say that 18 and 81 are now part of the sorted region. We must fix down, but not look at those two. And then we'll repeat that. We'll do another swap and a fix down, a swap and a fix down, a swap and a fix down. You're going to have to look at back when we did it. So when we insert, we push or pop, we have to do a fix up or a fix down to make sure before the push or pop on the priority queue is done, we're back to a heap. We use fixed up and fixed down to fix it. Okay, so with this one, we keep doing this process. So this is how Heapsort works. Heapsort says, hey, you gave me a thing, which I'm going to assume is a heap, and you gave me n, you gave me a size. How big is that array? I call my heapify on that. Heapify, remember, is this bottom-up fix down. So that's this process. Bottom-up fix down is heapify, that's O of n. So this step is our O of n bottom-up fix down. So that's O of n. We do that. So you gave us an array of stuff. We have no idea what order it's in. We do bottom up fix down to turn it into a valid heap. Then I know that basically n minus 1 times, notice how long this loop is going to run. It's going to run n minus 1 times. N minus 1 times, we swap index I with index 1, and then we call fix down, and notice here, this part is key, we lie about the size. Remember, our fix down, as we wrote it, accepts the size as the second parameter. So every time we do this, we're going to effectively lie about the current size. That way we hide the sorted elements at the end, and we don't let fix down modify them. Now, I'll say this again. This is not part of Project 2 Part B. I will probably still be helping people in office hours who try to do the heapify operation like this. This is too complicated. When you do the Project 2 Part B, we don't need this. We do not need this. In Project 2 Part B, though, this is going to be important. The bottom-up fix down is going to be important because one of the things you have to do in Project 2 Part B is a range-based constructor. Basically, I'm saying, hey, I've got a container full of stuff. I would like you to take my container full of stuff and throw it into your priority queue in the most efficient way possible. If you loop and push one at a time, you'll go over time. If you do a heap sort, you'll go over time because it's n log n. But if you do this, if you put the stuff into your internal data vector and then do a bottom-up fix down, it's O of n, and you'll meet the time requirements. Okay, so now we don't need heap sort for Project 2 Part B. We've got a summary here, and I've got one more thing important I want to tell you because you've got almost everything you need for Project 2 Part B. There's one more thing that we're going to talk in more detail about tomorrow, but I don't want to wait any longer to give you one last thing. So when we do, let's do the summary here, and then we'll do that one last thing. So when we look at a heap, we can take n elements. So this is the heap sort summary. So when we take n elements, we convert them into a heap. We do the bottom up fix down, that's O of n, and then we do the heapify. So we do the bottom up fix down, that's O of n time. Then we basically swap one at a time, calling fix down, that's n log n. Requires no additional space. It's never worse than n log n because we've got this loop. We've got this loop that runs, like we said, this loop is going to run n minus 1 times. We've got this loop that's going to run n minus 1 times. The work inside of that loop is O of 1 swap followed by O of log n. So if I do a log n operation n minus 1 times, that's where our n log n comes from. That's our heap sort time. Now, overall summary, this is important too. We're going to come back to the one last thing you need in a minute. So the priority queue is an abstract data type. We can build a priority queue in multiple ways. We can do an unordered PQ. This one, we gave you the code for it. We gave you 2 codes for it. We gave you unordered PQ and unordered fast PQ. Unordered PQ says, hey, let's just throw it at the back of the vector. I don't care. It's unordered. It's unordered all the time. But then when someone says, find me the top element, you've got to go, wow, I don't know where it is. Let's go find it. I got to go look at all the elements and find that one. It takes me O of n time. Now to remove the top element, we could do it in O of n time or O of 1 time. O of 1 time, we look in unordered PQ. The way we get the O of n time would be, hey, I don't know where the highest priority element is. Let's find it. I got to look at all of them. That's O of 1. Then I could replace the one in the middle with the one at the back. So if I've got something like 8, 16, 2, 9, 7, 3, I look through this, I find 16 is the highest value. That took me O of n time because I had to look at all of them. Then to get rid of it, I say, oh, well, let's just replace that 16 with 3 and do a pop back on the vector. It is unordered. So that's the unordered PQ. Sorted, which you have to implement. Sorted, it's O of n to insert a new item because it's got to be sorted at all times. If I told you, hey, I've got a data structure that's already sorted, I've got 1, 2, 3, 7, 9, 12, 16, and I would like to insert the value 4. Well, I got to find where it should go. Finding where it should go is a log n search, but then to tell the vector, put 4 here, that takes O of n time. So that's where you need one other thing you don't have is how do you find that correct location in log n time? You could write it yourself, you could write a binary search, or you could use the STL. STL has a function called binary search. It returns true or false. Not very useful. Better yet, you can use the STL's lower, oops, I cannot spell today. You could use the STL's lower underscore bound to tell you where it should be, and then you use the data vectors dot insert member function to put it there. The sorted PQ is all about using the STL. You want to make the STL do most of the work for you. Now the heap, when we say heap, we mean binary heap. The binary heap is, we're going to do log n push, we're going to do log n to do insertion, log n removal using fixed down. So our push is log n, our pop is log n, our top is O of 1. So we've got log n. Now think about the lifetime of stuff in a priority queue. You push it in, and at some point later you pop it out. So if we look at unordered versus sorted, it's O of 1 to get it in, and it's O of n to get it out or to look at it. In sorted, it's O of n to get it in, and it's O of 1 to get it out. It's always every element is O of n at some point in its life. In the binary heap, it's log n to get it in. Later on, it's log n to get it out. Its total cost is, so these are n and n. The total cost here is log n. Log n to push it, log n to pop it, and O of 1 to look at the highest priority. So those are the things you have to do for Project 2 Part B. We gave you unordered and unordered fast. You've got to write sorted. Sorted is literally going to come out to be like 6 or 7 lines of code using the STL. It's going to be really short. If you find yourself writing loops and stuff like that, you're not doing sorted the right way. You're not taking advantage of the STL. Binary PQ is basically turning these slides into code and dealing with the 1-based versus 0-based indexing, which there's tips on that in the project spec. Heapsort, not related to the project. Heapsort is just a nice, efficient O of n log n. It's never worse than that sorting algorithm. So that's everything for today's lecture, and we'll see you in a couple hours later.